I hope you're enjoying this as much as I am enjoying in recording these. And we did energy generation, distribution, storage, and talked about merging transportation into the system. Obviously, we also need to worry about grids themselves, because with renewables, intermittency, loads changing, trying to keep up with the load flows, it becomes important to have smart grids which are responding constantly to these changes in energy input and also changes in energy demand, plus also the idea of vehicles themselves being able to either take up energy from the grid, the load increasing unpredictably, but also able to add power to the grid when they are expected to be sitting idle for some time. So there was the grid to vehicle and vehicle to grid requirement, right? So the smart grid itself then becomes very important. So these are basically new ways of operating grids that will be needed. Deployment of distributed generation and associated distributed energy sources, DER, such as energy storage requires visibility to and control over this new paradigm. Basically, that means to be able to better handle the fluctuations of energy demand and energy input into the grid. It's good to have data to see what's happening, to be able to forecast and be prepared and also manage in near real time. A smart grid is a grid with intelligence to maintain and increase the efficiency and reliability of the grid. Reliability. So when you turn on the switch, you need power for light, for computer, for whatever else, right? Provide the grid operator with visibility and remote control of the system components through sensing throughout the transmission and distribution network. So if the grid is got a communication structure such that it knows, for example, if there is a big music festival somewhere and several thousand green music fans are going to show up with their hybrid cars and start plugging it in, then the grid operator needs to be able to see it and plan for it and operate it successfully and reliably. Provide two-way communication and controls to enable a path for grid automation and electricity market participation. So people who are producing energy with rooftops or community solar plants, wind plants, wind parks, and so solar parks, whatever, the grid needs to be able to smart enough to be instrumented with things like Internet of Things. I just threw it in there, but you can look it up. Maybe you already heard of it. So how does that change our picture we've been looking at? So going back to our baseline picture with the central generation, distributed generation, and the various users and various energy sources, and our hydrogen resource battery here, the smart grid would then add independent system operator capabilities, utility to the Tiger stations, consumer end here, and plug-in electric vehicles, and so on. So you can see that the grid has now become a little bit smarter. There is local control. So consumers themselves can have a little bit control on their use and feed it back to the grid, so the main grid operators also know that the system is going up and down in terms of demand and load. Okay, so just changed a little bit, just looks complicated, but it's not. We're just adding a few things each time. California provides an example of where the smart grid is emerging, with a focus on 4 major levels. Consumer level, which is what we talked of here. Facility management and control by residential owner, office building manager, industrial plant manager, or campus microgrid operator. These are places with substantial electricity use with varying loads during a class time versus evening times, for example, on a campus, especially when it has lots of commuters, thousands of students coming in and leaving, for example. Plug-in electric vehicle level, so automobile manufacturer and or utility management schemes control PEV charging, smart charging, and potential vehicle to grid energy storage recovery. So if it's a big manufacturer like Tesla sitting somewhere in California and wants to keep all the cars that are produced and sitting in the lot to be plugged in, then there is this opportunity to manage locally the smart grid. Utility level, where utility management and control of distribution system services and resources are to be managed. Independent system operator level, so independent system level operator, utility, consumer, and plug-in electric vehicles. ISO management and control of the full portfolio of grid services and resources, including electricity markets, to ensure that loads are balanced and that supply is reliable and sufficient to meet the grid dynamics, namely load changes and rate of load changes. It's not just that load goes up gradually from morning to the afternoon and then drops off. I'm just giving an example. But in a winter, for example, it could go up at night, but it can jump up rapidly. So the rate of load changes is also important. So electricity market refers to companies that do consolidation of power. So they are just like agents who sell power to consumers by buying it and consolidating it from distributed grid sources. Okay, as a part of the smart grid, smart metering, smart appliances, automated substations, and other distribution system upgrades, advanced sensing and controls, high-speed communications, smart inverters, and smart switches would be needed. I'm reading them because you should be aware of the concepts and the words, because you may not be electrical engineer as well, but you will know what these mean, right? Interoperability. Interoperability is an important thing, where a smart grid requires that various components of the system to communicate with one another. So you have now distributed grid as well as distributed energy sources with distributed users. Plug-in electric vehicles are running around. They are distributed users. At least a central controller operator communication would be needed. To achieve this, communication protocol, standards, and a robust communication infrastructure must be developed upon which vendors, utilities, and regulatory agencies can agree on and comply. Reliability and cost. The reliability of the system must be ensured without having excessive redundancy in order to minimize the overall cost of the system. Cost effectiveness obviously is always a concept that has to run through all of these. Data management, the collection of high resolution data is required to obtain an accurate picture of the system status and also verify the system load flow and transient models. Okay. As you can imagine, the more the data gets collected, the more methods like artificial intelligence and deep learning and machine learning will be brought in to manage and forecast the loads and their impact on the grid and requirements for rate of load change. Cybersecurity, as the system moves towards automation and remote control, the system must be secure enough through cybersecurity measures and encrypted communication. There is constant talk that new cyber terrorism activities will try to knock out grid systems of states and countries as a part of war or just terrorism. Too much change too quickly. Smart grid paradigm will dramatically change the roles of utilities, independent system operators, aggregators, companies which buy and sell, and service providers in a relatively short amount of time. Therefore, it's prudent to develop roadmaps and guidelines for the industry to follow and prepare for the revised roles. If this system keeps growing this way with smart grids, the smart grid is going to be the key control point for managing all these things. Development of wholesale electricity market. This is more of a economy level argument. First, the generating resource needs to establish an agreement with the utility to access the transmission system. So the contributors to the grid must establish agreement with the utility. Secondly, grid operators need to allow the distributed energy resources, or DERs, to participate in the market. This will present challenges since DER can be very flexible compared with the conventional generation and even renewable resources, and are located deep in the distribution system where independent system operators do not have visibility. So you could have many distributed energy resources that are wanting to contribute to the grid intermittently. May not be a steady source, and it may not be visible on the grid system. It may be coming way off, sitting somewhere in New Mexico as an independent solar park operator, or in Texas as a wind generator, and so on and so forth. Already there are several issues coming up in terms of people with rooftop solar trying to contribute to the grid and producing excess energy. Utility companies are not yet used to buying infinite excess energy from users, for example. Okay, so potential attributes of smart grids and microgrids: high efficiency, low greenhouse gas and criteria pollutant emissions, low operating costs, accommodation of grid ancillary and emergency services, ability to enable and expand evolving electricity sources, basically. Obviously, much research is needed to advance smart communications, controls, energy storage, high resolution and robust sensors, power electronics, load following, and high ramping of 24/7 clean power generation, smart plug-in electric vehicles charging and discharging, and management systems. In parallel, research is also required to establish and implement policies that support the development and deployment of the empowered concomitant electricity markets. So the markets themselves are obviously going to change as the energy becomes produced in distributed fashion. The grid is itself a merging of large-scale grids with microgrids and nanogrids, and utilities, independent operators, and consumers all being part of the system.